Hi everybody, welcome back to our operating system course CSC 669. So again, another video about PintOS. Last time I made a video to help you with project 1, and the idea was to show you how PintOS was switching between threads and do all of that in the debugger. So now I'm guessing that you are almost done with project 1 and we need to start working on project 2. So let's do another video here to show you, first of all, what project 2 is about. Okay, it's going to be about user programs, and then same thing, we're going to use the debugger actually to understand how system calls are working in PintOS. Okay, so let's start. So as usual, I'm going to start PintOS inside my Docker container. So this time I need to go source, and then the project 2 is inside user prog. Okay, so here what I can do is I can compile the code. Okay, hopefully this will work. Okay, and then now I can go in the build, and now I have the kernel for the project 2, basically. Okay. So here, something I can do, of course, is to run make grade, and that's going to run all the tests, and it's going to show me the tests that are not passing and so on, right? Right now, I haven't modified anything on PintOS, so of course I'm going to fail them all. Okay. I'm not going to run that because this is going to take some time. So instead, what I always do is to have some kind of a dump of the output here. So here, of course, what I can see is I can see all the commands that are tested. So let's look at the first command. And maybe here what's useful is to kind of see the difference between the first project and this project. Okay, so this is the first test of project 2. And let's go back to the first test of project 1. And you will notice the difference. Okay, so I'm just going to copy it here. I mean, I'm not going to run it. You see here, so in project 1, basically we're running PintOS. Okay, we tell basically that we're using box. And here we're running one test. Okay, and that was kind of the keyword for a test. Okay. Now, as you can see, we have a lot more things in the test, right? So here we have something like, it talks about a file system, it talks about a file inside test actually, okay? And then you have some kind of a name here, and then when you run it, it's actually have a -f, okay? It's even, I mean, it's even like, if I even copy the second one, actually maybe I will show you the second one. It's more, where is the second one? Here. Okay, let me. So here actually you can see the second one. It's like it has a -f run, and then here between quotes we pass. It looks like we pass some kind of a command, right? So that's will be the command, and that will be the argument to the command. Okay, so it's really different here. So why is it different? Well, it's because PintOS project 2 is about user program. So rather than running tests that in the past, it was kind of built with PintOS, and actually when we're compiling project 1, it was compiled with PintOS. This time we're going to run real user programs that are, compiled and that are written, compiled outside of the kernel, and then the kernel is going to run that program, okay, that binary. So here, if you want to do that, okay, we need to attach a file system to the OS. Right? Because this time the OS is going to look at the file system, read the binary file, and then execute that program. Okay? So that's why here we didn't need a file system before. So PintOS, didn't run with any file system, but now we need to actually have a file system. So this is actually explained in the documentation, but in a nutshell, what this does is like it creates a new file system. Okay? And then in this file system, it copies the file arg single, which is a binary, okay, actually that has been compiled, and then it calls it arg single, okay, and then it's going to run that file, that program, okay, that executable, and then it's going to pass this argument 1arg here, okay. So that's kind of a main difference, right? So now we are dealing with user programs. Maybe we can take a look at it. So if we go into the source in test. Test user prog, and then here actually argnown is derived from this argc here. And as you can see now, it looks like kind of a regular C program that you have been writing so far, which is like, it has includes some libraries, and then it has a main, and the main takes, of course, the number of arguments and then the argument list from the command line, right? And then you run it, and then you return, and that's it. Okay. So here you see, and the idea is like this is actually going to be compiled actually with any compiler, with GCC, for example. And then this binary here, it's going to be inside user prog, the build, and test. And here, this is actually, let me make this a little bit bigger. Here, you see argnon, that's the binary that has been compiled, right? And here, we're just like copying this binary into the file system. We attach the file system to PintOS, and then it runs, right? So let me run again. So here, I'm just going to run my first program, my first test. Okay. Actually, before I do that, let me show you. You can see actually this difference here. If you go to threads and then init, so inside, not inside the test, inside threads, init.c, you actually can see that. And this is on line 287, okay, in the run task function. You can see here the difference, right? In the past, when we were running the PintOS, after booting, what it was doing was running the command, and the command was given through the command line here. And then we're just like doing run test, and that was actually running the test. This time is different. So now user prog here is defined, and now instead we're actually going to process execute the task. Okay, so we can look a little bit at what process execute does. Okay, so now this time this is in user prog process.c, and we can see that process execute here. You see, start a new thread running a user program loaded from file name. Okay, so that's the kind of the novelty here in this in this project. Okay, so of course with that, as I explained in class, the idea is like we have user process being executed, and they are going to run in memory, but somehow isolated from other processes, but also, more importantly here, isolated from the kernel. Okay, and the way this process is going to interact with the kernel is going to be through system calls. Okay, and so I'm gonna explain you that. Okay. All right. So let's start first by just running this test, and let's see what's happening. So here, if I run it, first of all, so you can see, okay, so things, as you can see here, by the way, QEMU starts, and it starts with a file system. Okay, so it's QEMU create the file system and then attach it to PintOS somehow. Okay, so we boot PintOS and so on. Okay, all kind of information, and then at some point you see it's kind of executing argnon. Okay, and then argnon executes, somehow completes right away, and then that's it. It's off. Okay. So what happened here? It looks like it hasn't done much, right? If you look at argnon again, okay, and maybe let's open it again inside test, user prog args.c. Well, if you look at the program here, at least it's supposed to print some message, right? Begin and so on and so forth, right? It doesn't print anything. How come? Well, it turns out that here actually, in project 2, right away when you execute a user program, so yes, it's going to actually spawn a thread to run this user program, but then it terminates right away. Why? Well, we need to go back to actually maybe we can explain a little bit what's going on. Okay, so here, as you can see, when it let me go back to init.c. Just want to make sure. Okay, so you see init.c, it executes two things. Okay, first it executes the task, and then it's supposed to wait for the task to complete, right? So here, well, let's look at process. So here, process execute. So it does a bunch of things. What it does, it allocates memory at first. Okay, then it's going to copy the file, okay, which is on the file system, into the memory that we have freshly allocated. Okay, it creates a kernel thread, okay, to run that process, okay, and then that's it, okay. Now it has started. It has been put on the scheduler and so on. It's supposed to run, okay. But let's look at process wait. When you look at process wait, here's what it's supposed to do, right? So it's supposed to wait for a thread to complete, and it's actually just returning -1, meaning here the main thread actually is not going to wait for the process to execute, and it's just going to finish and then close PintOS, and that's why it's happening here. So the program actually has no time to execute. Okay, this is why if you read the documentation, what they ask you to do for now is to do the following. Let's have a while loop here. Okay, an infinite while loop. So if we do that, of course, PintOS is never going to terminate. Okay. There's something else they tell you to do. They tell you to change somewhere. Where is it? I can find it. They ask you to change the stack. Okay, let me find. Where is ESP? Where do they assign? Oh yeah, is it here? Setup stack. Yes. In documentation, they tell you, okay, at first. So the stack is going to start at physical base, but we do -12 just to ignore the arguments. Why? Because right now, I told you, right, you can code a program and then pass arguments to it, but this is actually not done in PintOS. You have to take care of it. But right now, since we want to actually pass this test that doesn't take arguments, we're just going to ignore them. So we compiled that. So once you have modified this line plus the line, plus in process wait, you put the infinite loop. Okay, process wait here. So now we should be able to recompile and see the difference. Okay, so let's go back one step. I'm gonna make. Okay, now it's better. And now let's let's run it. So let's run my test again. Okay, and now we can see there's something new. So first of all, it doesn't terminate. And that's on purpose, right? Because here we put a while loop, so actually the main thread is just like stuck on this while loop. Eventually this is going to terminate just because I put a timer on the command line, I think. Yes, 60 seconds. So after 1 minute it's going to stop. But right now we are stuck in this infinite loop, okay? Something else also happened. We got this written system call, but nothing else. So it looks like, you know, everything we had on args still is not printed. And instead we have this thing printed. So let's see, where is this thing come from? So I can do a search maybe on the entire PintOS just to see where it comes from. And here come from, well, actually here. Okay. It looks like this was the line that was printed. So let's look at this file. Actually, this file is quite interesting, right? It's very explicit, right? It's a syscall handler. Okay, so here, this is the handler that is going to be executed when there is the syscall interrupt. Okay, remember we saw that in the lecture, right? The way syscalls are invoked is by actually triggering a software interrupt. Okay. Something interesting here is like we can see actually that when this interrupt was registered, okay, and we can see that this interrupt is on x30. Okay, on Linux it's different actually, it's on x80 for example. So here on PintOS it's 30. And then here it's going to execute this handler, and this handler right now is doing nothing except printing a system call. Okay, so here it is actually. So we have PintOS, it's kind of executing user process, but then as the user process execute, it needs to do things like, for example, I mean, let's go back to args, right? But most likely, let's see, where is the test? User prog args. Most likely, it needs to kind of print something on the screen, okay, on the console. So that means here it's going to be a kind of an IO interaction. So that means a system call, and at least so there is this one, and at least and there are others. And at some point it's going to exit, and at some point it needs to tell the kernel, okay, I'm terminating, and please clean up after me, right? So at least here I can, spoiler alert, I can tell you there are two system calls that are not implemented and that we need to implement. Okay, so let's look at it a little bit from the point of view of the debugger. How would we debug this thing? So of course, the first thing I'm going to do is I'm going to run PintOS inside GDB. Okay, so here it's running inside GDB. So now what I can do is like docker run -it. My container name is named PintOS bash. Oh, docker exec, sorry. Okay, it already exists. Okay, so now let's go inside source. We are now in project 2 user prog, build, and so on. And again, I'm going to say PintOS GDB, and now I'm going to load the kernel, kernel.o. So, okay, so now as usual, okay, let's do a debug PintOS to connect to this. And then let's see, I just want to see what's happening here. I'm going to put a breakpoint at line 18 here in the syscall. Okay, so syscall.c line 18. Okay, if I do that, okay, now there's a breakpoint. I'm going to do continue. I can see things happening, and then I'm hitting the breakpoint here. Okay, so let's see, what's my stack trace? I look at the stack, and then I mean, what I'm going to see here is not surprising, knowing how syscalls work. It's okay, so we are on syscall line 18, and I can see that it comes from the interrupt again. No, that looks like project 1 where we're tracking like timer interrupts. Okay, that's actually the thing that handles the interrupt, and then some weird things, and then something like corrupt stack. Okay, so here you might ask, okay, who calls the interrupt? All right, so a few things here. So first of all, ignore the corrupt stack, okay? It's because actually GDB is a little bit lost. It's because of the virtual memory and so on, right? But we don't know who called the interrupt. Here, that's because most likely, I mean, what we suspect is that it's the program argc, I mean argsc here. It's this program that somehow called this program here that somehow called the interrupt. Okay, but here the GDB is not able to actually trace that. Why? Remember, right? Here we have started GDB, and we are kind of when we started here, you see, we read the symbols from kernel.o, right? So everything which is within kernel.o, GDB knows how to handle it. But here the program is not inside kernel.o. The program is outside kernel.o, right? On a file system, and GDB doesn't know it. So actually, you can load that program additionally. So it's load user symbols, okay? And now you need to pass, let's see, you need to pass test, it's user prog slash args known. Okay, I think it's that. Perfect. So here I've loaded extra user symbol. And now if I do again backtrace, I have a little bit more information this time, okay? And here I can see that here it's actually lib user syscall.c. Okay, so let's look at that. It's lib. Okay, we haven't seen this file before. Lib syscall.c, lib user syscall.c. Okay, and it's line 123. Okay, 123. Okay, so that's interesting. So that's the line basically that call that generate the interrupt actually. Okay, so here it's like a function write. Okay, so it looks like a write fd. Okay, and that sounds like file descriptor. There's a buffer and the size. Okay, we're going to write stuff inside a buffer. And here, let's look at this function syscall3. Actually, syscall3 is defined in the same file. Okay, and it's up there. Okay. Maybe here I'm going to make this bigger to avoid this kind of stuff. So what's syscall3? Syscall3 here, look at it. So even if you're not familiar with assembly, actually you can see a few things here, okay? So it looks like it's pushing things, okay? And actually here, this is pushing stuff to the stack, okay? And here, as you can see, there is like int x30. This is our interrupt, okay? So fine, we find our suspect here. So this is a function that was called and that triggered the interrupt. Before triggering the interrupt, of course, it pushed the arguments onto the stack. Okay? So all right, so we see that it's actually this file that triggered the interrupt. But let's see, who called this file? Okay, we suspect it's going to be argc, right? But just in case, let's see. Let me go back to the to my debugger here. I'm gonna kill the program, and I'm gonna restart it. Okay, I'm gonna remake the connection, debug PintOS, and this time, let's see. So I know it was on write. I'm gonna put a breakpoint actually on this line 121. Okay, so let's do that. I'm gonna put a breakpoint on. So it's inside lib/user/syscall.c. Am I right in the spelling? And line 123. Okay, so now I have a breakpoint. Actually, now I have two breakpoints, and let's continue to that breakpoint. Okay, I've reached my breakpoint number 2. I'm actually inside write fd1, so now I can see the arguments. 1, the buffer is this, and the size is 13. Okay, so most likely here, let's see. So here, let's look at the trace, at the backtrace. So now the backtrace is different, right? And actually, that's something interesting here. If you remember what I talked in the lecture, there is a difference between the user space, the user mode, and the kernel mode. Okay, actually here, because we are still executing the program, okay, the user program, we are still in user mode. And it's going to be after the interrupt. Actually here, when I was debugging earlier, here I was actually in kernel mode. Okay, I was inside the kernel executing the interrupt handler. Okay, so now I'm user mode here. And I can see actually where this was called. So it was called actually by a library. Okay, and it's libc. So let's look at this test libc. So if I go to test lib, no, it's not lib, it's just test libc inside /test/lib. Okay, that's a libc, and here it was the line 24. Okay, that's my write. Okay, and then again, who called this libc? Okay, well, this libc at some point was called by the same libc, but eventually was called by argc15. And if we go back to argc15, here you go. Yeah, we are here. Okay, so here what's happening is the following. So my user program called message. A message is some kind of a printf in C, right? So here message, basically it's like, okay, can you print that message? So this actually requires to talk to the kernel, because the kernel is going to do the input-output on the console. So this actually is calling a libc, and then the libc actually does the interrupt, and then there is an interrupt handler, and the interrupt handler is going to execute the syscall. But right now, it's not there. It's not in the syscall. Okay, so here, let me go back to where we're supposed to do some work. Here, we are supposed to implement write, okay, and to write on the screen. Basically, we have the idea that write is going to be about calling printf, right? Because printf is a function that we have available at the kernel to actually print on the console. Okay. Okay, but maybe here, let me continue in the debugger. All right, I'm back at the handler here. Once I'm at the handler here, okay, right now I'm calling the handler. Again, as I told you, right, when you are doing a syscall, every system calls are going to trigger that that interrupt, right? So here we are going to process all of the system calls independently. Oh, by the way, how many system calls are there? Well, for that actually, you have the list inside syscall.c, .h, sorry. No, it's not there. Oh yeah, it's inside. We're going to see that actually. It's inside, not in test. It's inside lib, syscall, and all.h. Yes. Okay. So as you can see here, this is all the syscall that you have to implement actually for project 2, right? So there is about a dozen of them, right? And here's our suspect that we need here, syswrite. Okay, but still, when I'm reaching that point here, okay, let me close all of that now. When I reach that point, how do I know which syscall to execute, right? So let's see, is it inside this F frame here? Well, let's look at it, right? P-F, we can look at it, and it has, of course, all kind of information about the stack pointer, the instruction pointer, the registers, and so on and so forth. We can see actually here the interrupt number and stuff like that, right? But this kind of data structure here, this is the normal data structure that every interrupt handler is getting, okay? So the information is not there directly, okay? But remember one thing, when the system call was invoked, where did we push the arguments and so on, and the name of the system call that we wanted? On the stack. Which stack? The stack of the program that was running. Okay. Do we know where is the stack? Yes, actually, because this actually inside the interrupt frame, we can see which program was interrupted at when this syscall was triggered. And we can see here, where is it? The ESP. Here, okay, that's our stack pointer. Okay? So here we can see that well, that was a stack pointer before it was interrupted, and we know that the arguments are there. Okay, so well, let's look at it. So again, you have to look at the documentation that explains exactly how the arguments were pushed, but let's actually look at it a little bit. So here, what we can do at first is like, well, let's look at the first 4 bytes of the what's on the stack directly. So if you do that here, we're going to see that you have the number 9. What's that? That's actually the ID of the system call. And why 9? Well, again, you have to go back to actually the thing that I just showed you. Here, 9, if you look at this enumerator here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. Write a file. That's our write. Okay, so that's how we know actually which system call was invoked. Okay, so that's directly in the first 4 bytes of the stack. And then what's following? Usually what's following is the arguments. Okay, so let's look at the first argument. The first argument here, well, it's 1. What is this 1? Well, again, let's go back a little bit to where it was called. If you remember correctly, oh, I shouldn't have closed it, but well, actually, let me see. It was inside the libc24. No, actually, I can just go to libuser system calls. See, okay. So here, okay, where is the right? Right here. We have 3 arguments. The first one is supposed to be a file descriptor. Actually here, this one, it's the file descriptor. Okay. The other one is supposed to be an address of a buffer. Okay. And the last one is supposed to be a size as an int. Okay. So let's look at it. So here now we have the file descriptor. This one. So now let's print so we know it's an address, right? So here I'm passing the format. Here I'm looking at the address, which is stored well, at the stack pointer, we pass like 4 bytes and 4 bytes after here. So now this is the address of the buffer. Okay. Well, actually, can we see what's stored right now inside this buffer? Well, yes. What we can do is the following. Okay. We can, no, we're going to assume it's a string. I mean, we know a little bit, right? We have traced it. It's actually a string. And here I pass the address of the buffer, and now I can see, here you go. You see, args begin. That looks good, right? That's exactly what I had inside. Again, no, I shouldn't have closed it. Where is it? So it's inside test, args, user progs, args, okay? And it's actually, well, actually we are here. Okay, it has passed the begin, it looks like. Okay. Oh, no, it's begin, sorry, begin, here. Okay, so it's there. Then what else? Well, Well, let's look at it. What's even after that? The third argument. Here it's 13. And 13 is the size. And yes, if you look at the string, actually, it has actually 13 characters. Okay, well, we have everything, right? Now, the only thing we need to do, the only thing, it's the beginning, it's just the beginning. We need to kind of extract all of this data from the stack pointer stored in the frame. We extract all of that. We do some kind of a giant switch, and we say, okay, now let's execute write. And then write, we basically take the arguments and then do some printf, okay? And if needed, we return something and so on, right? And we're gonna do that for all of the system calls, okay? At some point, some system calls will require you to, to have the command line arguments actually of the program and so on and so forth, okay? But that's coming later, okay? Hopefully, with that, you have everything you need to start implementing your first system call, okay? That's it. Well, good luck with project 2. Bye.